Hello everyone, my name is Gabe Heffner. I am presenting for my Math 540 class, History of Mathematics, and today the topic will be Pythagorean mathematics and philosophy. A little background about me is I major in computer science and mathematics as well, so I'm happy to be here today. All right, so first things first is who were the Pythagoreans? Pythagoras lived around 570 to 495 BCE and was both a philosopher and a mathematician. He founded a community in Croton in southern Italy where his followers lived in a communal and disciplined lifestyle. For the Pythagoreans, mathematics wasn't just a tool for solving problems, it was part of a religious and moral way of life. They believed that studying numbers could reveal deep truths about the universe, and this group treated mathematics with almost sacred importance. Pretty much, they believed mathematics were one of the main causes to the answer to life and all that jazz, and also the meaning of who you are as a person. They believe that could be found through mathematics. Now, the mathematical environment of ancient Greece, this is pretty much where Pythagoras was based and where he grew up and where he learned most of his math and taught. So the first things first is they shift from practical math to deductive reasoning. That was one of the biggest changes, one of the biggest start of changes of math history, because they usually were so logical and now they use deductive reasoning now. Before the Pythagoreans, Greek mathematics was heavily practical, influenced by Egyptian and Babylonian methods. Those cultures used math for construction, trade, and astronomy. But during Pythagoras' time, Greek thinkers were shifting toward reasoning, not just calculation, which is pretty much what I just said. And then Pythagoreans helped formalize mathematical thinking as well, and it was more of an emphasis on proofs rather than computation altogether. So, which is pretty much what math is when you get down later in the line. You know, you start with a squared plus b squared equals c squared, and then now you're writing proofs, which is great. But yeah. We'll go to the next part. This is Pythagoras' philosophy. All is a number, or all is number philosophy. And pretty much he's just saying numbers rule the universe. He believed that numbers were the main focus for, I guess, the universe and how everything works and how everything ties to fate and stuff like that. Pretty much he said a core belief of the Pythagoreans was that all is number. They believed numbers were the fundamental building blocks of reality itself. Odd numbers represented masculine qualities. Even numbers represent feminine qualities. They also discovered that musical harmony is based on numerical ratios like 2 to 1, 3 to 2, 4 to 3, and which reinforced the idea that nature is mathematical. Their symbol, the tetratus, symbolized universal order, and then then Pythagoreans viewed mathematics as spiritual and moral. So, yeah, that's it for this philosophy. I'll move on to the next slide. Pythagoras helped discover irrational numbers. So irrational numbers are pretty much a belief all quantities are ratios of whole numbers. So an irrational number is the definition of it. An irrational number is a real number that cannot be written as a simple fraction. Irrational means not rational. An irrational number can be written as a decimal, as endless non-repeating digits to the right of the decimal. And this discovery attributed to Hippasus, I think that's his name, and the Pythagorean was punished because irrational numbers threatened their philosophical system, which threatened their belief of whole numbers and all that. This discovery pushed Greek mathematics to develop more rigorous methods for dealing with magnitudes. And it also means like the diagonal of a square with side length 1 has length square root 2, and square root 2 is not rational. So this was a shocking discovery because it contradicted their whole belief in whole number harmony. So yeah, pretty much this is one of the changing points in major developments in Greek math because it contradicted Pythagoreans' belief of whole number harmony. Here's the Pythagorean theorem, which is one of the main theorems that we know to this day. It's used a lot in geometry. Probably the biggest thing to know in geometry is the Pythagorean theorem. But the Pythagorean theorem is c squared equals a squared plus b squared. It was known in Babylon before Pythagoras. Pythagoreans provided first deductive proof, and then they provided the statement a squared plus b squared equals c squared, which is central to Greek geometry. And pretty much the definition of the theorem is, the theorem states that for a right triangle, the square of the hypotenuse equals the sum of the squares of the other two sides. So this result became a foundation of Greek geometry and remains central in mathematics today. Yes, let's go. All right. Here we have the geometric proof, which is pretty much the rearrangement, and it's pretty much just showing you how the proof is, like how it's made and how it works. So I have this diagram that pretty much just shows like a squared plus b squared equals c squared, and it's showing how it makes this bigger square in the middle. So one of the classic proofs of the Pythagorean theorem involves rearranging shapes. You create a large square with side length a plus b, and then divide it into 4 identical right triangles and a central square. Comparing 2 different decompositions of the shape shows that the area of the inner square must be c squared. This demonstration highlights the Pythagorean emphasis on geometric reasoning and deductive thought. So the next thing is Pythagorean triples. We did a little unit on it when we were working, and we had a quiz on it for Math 540. So this is one of the main things that Pythagorean also developed. The Pythagoreans also studied whole number solutions to the equation a squared plus b squared equals c squared. These are known as Pythagorean triplets. For example, the famous 3, 4, 5 triangle. Using 2 whole numbers m and n, you can generate primitive triples using a formula. And the Pythagoreans explored these patterns because they connected geometry and arithmetic, which were both central to their worldview. And there's some examples right there: 3, 4, 5, 5, 12, 13, 8, 15, 17. And this is pretty much showing the generating Pythagorean triples. It shows the method and all that jazz. So now we have geometric constructions, pretty much what they constructed with Pythagorean's viewpoints and stuff like that. The Pythagoreans used only a compass and straight edge in the geometry. They investigated classic problems such as doubling the cube, trisecting the angle, and squaring the circle. Many of these problems were later proven impossible under classical rules, but Pythagorean work helped set the stage for later Greek geometry. And then these construction problems also reflect the belief that geometric shapes held philosophical meaning. Yeah, so like in your geometry classes, you'll usually like use a compass and a straight edge to find shapes and to find areas and perimeters. So that's what Pythagoreans would usually do. So yeah. And then now we have their influence on Greek mathematics. Pretty much the Pythagorean focus on proof became the foundation for Euclid's Elements, one of the most influential works in history. Euclid's axiomatic method, starting with definitions, postulates, and logical deductions, is deeply rooted in Pythagorean ideas. Their approach shaped the structure of Greek mathematics and influenced countless later mathematicians, including Archimedes and Apollonius. And this is pretty much the start where they did most of their emphasis on deductive proofs. So they switched from logical to deductive reasoning, and this is pretty much where they started showing their deductive proofs and all that jazz with the Euclid Elements, and pretty much where proofs started overtaking calculation for the future of mathematics. All right, so then we have the influence on number theory. The Pythagoreans also advanced early number theory. They studied figurative numbers like triangular and square numbers by arranging pebbles into geometric shapes. They also investigated perfect numbers where the sum of the proper divisors equals the number itself. Their ideas laid early foundations for number theory, inspiring developments in modular arithmetic, algebraic number theory, and even modern cryptography. So here's a studied figurative numbers, and then investigated perfect numbers, and then they also had early development of number patterns. And then I think the cryptography is one of the main things that I like to focus on, because that's actually really cool that Pythagoreans were able to influence that. I also think that I might take a class of number theory in the future, So hopefully that can, hopefully by researching this, I'll be able to get a lot of help with it. All right, then we have influence in other arts. So they had influence on numbers form the fundamental structure of reality, which is pretty much the definition of Pythagoras ideas or Pythagorean ideas. It also taught that harmony in nature is expressed through mathematical relationships. They believed that numerical ratios explain everything from music to cosmic order, showing that mathematics was not just a tool, but a guiding principle of reality. Their interpretation of the Pythagorean theorem reflected this worldview, linking geometry to deeper truths about balance and proportion. This integration of mathematics, metaphysics, and harmony became a foundation for later Greek philosophy and continues to influence how we understand the relationship between math and the natural world. So I think one of my favorite things about this slide is probably the music area. Math can affect so many things, and I'm glad that it affects music as one of the main things, because so that's what I'm really thankful for the Pythagoreans for. All right, then we have modern scientific applications. So we have they affected Pythagorean ideas are still at the heart of modern mathematics and science. In geometry, the distance formula is just the Pythagorean theorem expressed in coordinate form. In physics, the energy momentum relation from relativity has the same structure as the theorem. So I'm guessing both of these are the same structure as the a squared plus b squared equals c squared theorem. And then engineers use the theorem daily in building design, navigation, and surveying, which makes sense because they gotta, if you're like, for example, if you're like a mechanical engineer, you're definitely gonna be using the Pythagorean theorem a lot to create the shapes and stuff you need to design the machines. In computer science and machine learning, we rely on Pythagorean style distance formulas to measure similarity and train models. Yeah, that's the same thing with data science. Pretty much distance metrics to help you find your data and also train the models that you need to use for the data. And then also you have even modern music theory still depends on the numerical ratios the Pythagoreans discovered. Yeah, so it connects back to music once again. All right. So then pretty much we have the summary. Pythagoreans unified math and philosophy, developed deductive proofs and geometric reasoning, discovered irrational numbers, ideas still shape math, science, and technology, and pretty much to summarize, the Pythagoreans blended mathematics with philosophy in a way that changed history. Their ideas became the backbone of Greek mathematical culture and still appear in the math and science used today. Their belief that the universe is fundamentally mathematical continues to shape our scientific worldview. And then also, I'll show y'all the references real quick, and then I'm gonna show y'all a example of how to actually prove Pythagorean's theorem, and actually I'll show you an example of how to actually use it as well. So here, these are the sources I use to find all my information and stuff like that. So we have Burton, History of Mathematics, Katz, The History of Mathematics, which is just another author. And then we have Stanford Encyclopedia of Philosophy. We have Heath, A History of Greek Mathematics. And then Exploring the Mathematical Philosophy of Pythagoras, Theorems and Ideas, which was a Greek history hub. And here's a link to the reference pages and stuff like that. So real quick, I'm gonna write how you would solve this right triangle real quick. So on the slides, we had an example, this one, for the Pythagorean triples. We have 3, 4, 5. And then, or actually, I'll just do a normal example. So let's say we had a triangle, right? And we want C, and we have A equals 5 and B equals 6. So then for this, we're gonna have 5 squared plus 6 squared equals C squared. So now we're gonna have 25 plus 36 equals C squared. So now we can add 25 plus 36. 1 plus 2, 3 plus 3, 61. So then 61 equals C squared. So now we square root both sides to get C. So C equals the square root of 61. And that is how Pythagorean's theorem works. So that's pretty much all I have for today. Thank you for watching. Thank you.